but they're not.
And then we add a link from the seminar to this one.
So, like upload that to a Google Drive, is that?
No, you have it in the cloud, right?
No, not as cloud, actually locally.
Okay. Upload it on YouTube.
YouTube, I see, sure.
And ask Ryan, because he has a channel where he collects all the internet talks.
So I suggest we put it in the Google Drive, and then Ryan can access it there and put it publicly on the official channel.
Got it.
Sorry.
Did you have a good lunch?
Yeah.
Yeah, and talk with Mo about the large language model.
Okay. Yeah, so I didn't send out the announcement yet, but most CIDR submission was accepted.
Oh, it was? Congratulations.
Great. Yeah, we need to analyze this and put it on the news. Okay, so I think it's time to stop. Oh, here's my map. Okay, so we are only missing Ryan, but he will catch up. Okay, so it's time to start. Welcome everyone. It's my pleasure to introduce today Haoran Ding. Haoran is a student at Yale University, and we actually met at SIGMOD. Haoran works on query verification, checking if two SQL queries are equivalent or finding equivalent SQL queries. This is a problem that we also worked on, so this is where the interest comes from. And we have here both our regular database folks and also some guests from the Partser group who are very interested, much more so than we are in verification. So Haoran, please take it away.
Thank you for the introduction of them. I'm very glad to have the opportunity to share my work about automated verification for equivalence. Proving SQL equivalence is a very fundamental problem because it can be applied in many research areas. For example, SQL write is a typical optimization technique in database. Given an original query, the database usually needs to rewrite it into another equivalent but faster query. Equivalent means that these two queries should always produce the same result within the same input tables. And furthermore, the materialized view is like the cache in the database. For every current SQL queries, the database will check whether this query has been executed before. If it is, it will reuse the cached execution result for the previously executed equivalent SQL queries. This can reduce the execution latency. And for the bug debugging area, some workers try to generate some equivalent SQL pairs and execute these two equivalent SQL queries in the same database. If the database does not have bug, these two SQL queries should produce the same result. Otherwise, they will find some bugs in the database. So SQL equivalence is the foundation of some important research areas. However, existing verifiers have weak verification capabilities. The basic process of the verification consists of two main parts. The first part is the translator. The translator is responsible to translating each SQL queries into an algebra formula called F. So if we want to prove that the query Q1 is equivalent to the query Q2, we can formalize into a formula, which is the algebra of F1 is equivalent to the algebra F2. After that, we get a formula, and existing verifier will design some decision procedure to check whether the formula is true. And the existing method is that they propose some normalization algorithm to normalize these two algebras into two normal forms. After that, existing verifiers will compare the syntax structures of these two normal forms. If they have the same syntax structure, the verifier will say that they are equivalent. Otherwise, the verifier will treat them to be not equivalent. But the main limitations of the existing work is that equivalent formulas may have syntactically different normal forms. For example, these two SQL queries are equivalent. The query Q1 is select X from R where X is more than 30 union or select X from R where X is less than 10. So you will see that this query 1 will return all X that is less than 10 or more than 30. So the query Q2 is select from R where X is more than 30 or X is less than 10. So these two queries are equivalent, but they have very different syntax structures. The query Q1 uses union all and it has two subqueries, but the query Q2 does not use union all. It does also not have subquery. So existing verifiers cannot verify the equivalence of these two equivalent SQL queries.
So Howard, just clarify. So here the crux is that these two predicates are disjoint. They're exclusive. And this is why the union is the same as taking the OR.
Yes.
Otherwise, they would not be equivalent.
Yes, exactly.
Okay, good, thanks.
And because of these limitations, you will see that for these two test sets, existing verifiers can only prove less than half of the test cases in the kernel data and the stack pixel. So you will see that the main limitation is that these algorithms depend on the comparison of syntax structures. So our basic idea is that we should not only consider syntax structure, we should incorporate the semantics of SQL queries into our verification algorithm. Our input is also two queries, Q1 and Q2. And our verifier SQL solver will first translate these two SQL queries into extended U-expression, which is an algebra used to model the semantics of Q1 and Q2. And after that, we design a semantics-based decision procedure. We do not check the equivalence of these two expressions by comparing syntax structures. We will convert the formula F1 equals to F2 into a first-order logic formula. And then we can automatically verify the formula with SMT solvers. SMT solver is a typical proof tool that to prove first order logic formula. It will output whether the formula is true or false. And in our evaluation, we can cover all test cases that can be proved by prior verifiers, including UDP and SPACE. And we can pass all test cases in the kernel set test set. And the existing verifiers can only pass less than half of these test cases. So because our SQL solver has two main parts, the translator and the decision procedure, so I will first introduce our translator. I will first introduce what is U-expression, because U-expression is not proposed by our work. It was proposed by the work of Dan Sushi. And it's a models SQL queries with multiplicities. It defines the U-expression to be a function ft. The input t is a tuple. And for every tuple t, the function ft will return the multiplicity of the tuple in the query's output. For example, here is a table R here. It has two columns. One is X and one is Y. The query is select star from R. It will return all the rows in the table R. And if the input of the U-expression is 1, 2, the U-expression should return 2 because there are two rows, 1, 2 in the table R. And if the input is 1, 3, the U-expression should return 0 because there is no row in the table which is 1, 3. So after defining what is U-expression, you will see that the problem of whether Q1 is equivalent to Q2 can be translated to proving this formula. For every tuple T, the result of the first U-expression should always be equivalent to the result of the second U-expression. But the expressiveness of the original U-expression is not enough. It can support selection, inner join, projection, union, but it cannot support some other important but commonly used SQL features, such as out-join, norm, aggregate functions. So our work extend the U-expressions by introducing more operators and introducing more translation rules. And the details can be found in our paper. After our extension, we can support all test cases derived from the KL set. And we are also the first verifier to support concrete aggregate functions, Scala subqueries, and some other commonly used SQL features. And I will use some examples to introduce the details of the UV pressure. And for the first SQL query Q1 is a select star from R because it will always return all rows in the table R. So the UV pressure is defined to be RT. I use the lowercase r to represent that RT is an uninterpreted function rather than table R. And this uninterpreted function returns the multiplicity of the tuple T in the table R. And we can reuse the query Q1 to be the subquery in the query Q2. Q2 is Q1 union of Q1. So it will return all the rows in the Q1 and union the result of all the rows in Q1. So the use pressure of the query Q2 is RT plus RT. And you will see that we can reuse the use pressure of the Q1 RT here. And the third example is select a distinct star from R. The distinct means that we should remove all duplicate tuples in the result. So this use pressure is defined to be this formula. ITE here means if then else. The first parameter is a Boolean value. It means that if RT equals to 0, the ITE will return 0. Otherwise, it should return 1. This is the meaning of the ITE if then else. So you will see that if the tuple T exit in the table, the use pressure should always return 1 because the query will remove all the duplicate tuples in the result. Otherwise, it will return 0, which means that the tuple does not exit in the table down.
A quick question here to the people, egglog experts in the room. Does egglog support such expressions, conditional expressions? It does? I think so. Cool. Okay. Perfect.
Okay, and I will give a complex example here. It's a projection on the table R. Select X from R. So according to the definition of use pressure, assume the use pressure is FT. FT should return how many rows that satisfy the two requirements. First, the row is in the table R, and second, the column X of the row should be T. This is the definition of the use pressure FT for the query select X from R. And if we want to calculate the use pressure FT, there is a pseudocode here. Initially, we set the total number to be 0. And for every row in the table R, if the column X of the row equals to T, we should increase the total number by 1. And finally, the use pressure will return the value of the total number. This is the calculation of the process of the use pressure FT. And if we want to formalize this pseudocode to be a formula, it can be represented by this formula. FT equals to GAT plus GBT plus some other formulas. And here, the A, B, C means possible rows in the table R. And the function G, row T means that if the row has the column X equal to T, the function G should return 1, otherwise it should return 0. So because we want to prove that two SQL queries are equivalent for any possible input tables, so we need to consider all possible tables, which means the table may have arbitrary data, may have arbitrary size. So we need to enumerate all possible rows to consider tables with arbitrary data and unbounded sizes. So this formula may have unbounded length. But we cannot write unbounded length in the code. So we introduce a summation symbol here. This is ft equals to summation t1 g t1t. It means that it will enumerate all possible t1 and calculate the sum of the g t1t here. And the value of t1 belongs to the set here. The set contains all possible rows A, B, C, D. And because we need to consider all possible tables, so this summation domain is unbounded. It has unbounded elements.
So another comment for the egglog people. I don't think egglog can support this. This is a higher order operation, which takes as it doesn't take as input values in your algebra. It's not a sigma algebra operation, but it takes as input g, which is a function. You need the ability to construct these functions and then to apply this summation operation to the function to get back a value in your domain. So I think this is very SQL is very demanding for egglog and for Kali and for many other database applications.
I think this is not doable in the in the plain egglog, but you can do it with the Rust API bindings.
So there is a way.
Yeah.
Okay, so let's
Okay. After defining the use pressure, I will introduce our semantics-based design procedure for use pressures. And the main change comes from the unbounded summation in the previous slides, because the unbounded summation is the sum of unbounded elements. But we want to translate the use pressure into first order logic formula, but first order logic cannot represent the sum of unbounded elements. Although first order logic has quantifiers, universal quantifier, accident quantifier, but they cannot represent the sum of unbounded elements. So deciding the equivalence of extended use pressures is undecidable. This is the main change we want to address. And our insight is existing theory called the Leer-Star theory. And this is the first author is a professor at Yale, who is our co-author. And Leer-Star theory was proposed to reason about the series of multisets. This is very similar to the problem we want to address, because tables can be treated as multiset. And to handle multiset with unbounded sizes, this theory can represent the sum of unbounded number of integers. So we find that this Leer-Star theory has some limits, has some similarities with the problem we want to prove. I will first introduce what is Leer-Star. Leer-Star has two parts. The first part is Leer, the second part is star. So I will first introduce the star operator. Star operator is an operator performing on a set. Assume that there is a set S, and S star will return a new set. And every element in the new set is a linear combination of arbitrary numbers of elements in the set S here. So the formal definition is shown in this formula. S star is a set. This set is a set of vector here. And the vector is the summation of arbitrary vectors Vi, and every Vi belongs to the original set S here. So you will see that this formula represents every vector V in the set S star equals to the linear combination of vectors in the original set X. And it can be the linear combination of 0 vector, 1 vector, 3 vector, n vector, and the n here can be an arbitrary integer.
So this is the positive linear combination of vectors from S.
Yeah.
It's also called the conic closure or the cone closure because the result is a cone.
Yes, it's a closure. And for example, if the original set S has only one element, which is 2, then the S star you can have such elements. First, the element can be the linear combination of 0 element in S, which is 0. And then it can be 2. And then it can be 2 plus 2, can be 2 plus 2 plus 2, can be 2 plus 2 plus 2 plus blah, blah, blah. And this is the set of S star. And
so the lambdas, are they supposed to be integers?
Yes, lambda should be integers.
Interesting. So this is not the positive linear, it's not a closure under positive linear combinations, but only under integer positive linear combinations.
Yes.
Okay, so it's not a cone. The result is not a cone.
So we'll see that the S star is actually the set of all even integers. And if the S has 2 elements, one and 2, we can construct S star. So the first element is 0, and then the second element is 1, 2, 1 plus 2, 1 plus 1 plus 2 plus blah, blah. So this is actually the set of all integers. And after introducing star operator, we introduce the second part, Lie. Lie means linear integer array arithmetic, which means a formula involving integers. It represents the conditions that some integer variables should satisfy. It can use operators plus and some comparators more than equal to less than. These are all linear operators. So x equals to 3 is a Lie formula. X more than 100 is a Lie formula. And x plus y equals to z is also a Lie formula.
Question.
Okay.
Are there negative numbers in the Lie theory?
It does not have negative integers. The original Lie star does not allow negative integers.
And to allow subtraction?
It does not allow it, but we have proved that we can support it because subtraction can be translated to be plus, right? X minus y equals to z is x, yeah, here. This is equal to x equal to z minus y, right?
But it does not have a negation operator, right?
The original theory does not have negation, but we prove that we can also introduce negation into the Lie star theory. Okay, and after introducing these two parts, here is the normal form of a Lie star formula. Lie star is a linear integer arithmetic with star operators. So the formula means that there exists two integer vectors u and v, and u and v satisfy the Lie formula F1. And the vector v belongs to the set constructed by a star operator here. And every vector in the original set satisfies the Lie formula F2 here. And here is the example. This is the Lie star formula. We assume that the vector has only one element. There exists a variable v equals to 1, and v belongs to this set. Then you will see that this set is constructed by performing the star operator on the original set. The original set has only one element, which is 2. So we have introduced that this set constructed by the star operator represents the set of all even integers. But the first part of the Lie formula requires that v should equal to 1, but 1 is not an even integer. So this formula is false. And Lie star formula has a very important and good property. Two formulas are equivalent means that these two formulas are both true or they are both false. And the pre-work has proved that for every Lie star formula, we can automatically convert it into another equivalent Lie formula. And the Lie formula is actually a first-order logical formula, which can be directly solved by existing prover. So here is the example. This formula represents that v equals to 1 and v belongs to this set. It is actually equivalent to this formula. You will see that we do not need to use star operator here. We just represent that v equals to 2 times lambda. This can also represent that v is an even integer. These two formulas are equivalent. So this property is very important because Lie star formula can represent the sum of unbounded elements. But even if it is powerful to represent the unbounded summation, it is still decidable and can be directly solved by existing SMT solvers. So our insight is that maybe we can model the unbounded summations in unit vectors via the Lie star theory. And we can rethink what we need and what Lie star theory can do. We need to reason about tables with unbounded sizes. And the Lie star theory was proposed to reason about a multi-set with unbounded sizes. Second, we want to model the unbounded summations in unit vectors, and the Lie star theory can use the star operator to represent unbounded summation of integers. And the third, we want to convert the unit vectors into a first-order logic formula. And the pre-work has proved that the Lie star theory can be converted into an equivalent first-order logic formula. So we can provide a principled way to reason about unbounded summations based on the Lear star theory. And after we use the Lear star to bridge the gap between unit pressures and first logic formulas, the workflow of SQL Solver is shown in this picture. The input is two queries Q1 and Q2. After we translate them into an extended unit pressure, we translate the unit pressure into a Lear star formula. And then we can translate the Lear star formula into a first logic formula. The first logic formula can be directly solved by existing SMT solvers. And the solver will tell that, okay.
This is a small question. I get the integer arithmetic. I'm just curious if linear has any meaningful restriction here. So if you had like a self join of like a table with itself maybe multiple times, does that violate in some way like the linearity of linear integer arithmetic, or
violate linear? I will show you later because join will introduce multiplication, and multiplication is not allowed by the original Lear star theory.
Oh, cool.
Yeah. So life seems to be very beautiful if we use the Lear star theory. It seems to be a free lunch, but really, we find that there is still a big gap between the Lear star theory and the unit pressures, because unit pressures will result in some non-standard Lear star formulas. First, in Lear star, the normal form only allows single level summation. It means that you can only represent the summation of unbounded integers. You cannot represent the summation of integers. But unit pressures may use some nested level summations, which means we need to calculate the unbounded summation of unbounded summation. And second, Lear star is linear integer arithmetic. It only allows a linear operator, but unit pressures may use some nonlinear operators such as multiplication. Yeah, this has been found by you. And finally, Lear star is linear integer arithmetic. So you can only use integer variables in the Lear star formula, but the SQL query often operates in tables which have string data, which have data or some other data types. And these data types are not allowed in the Lear star, but we need to represent them in unit pressures. So SQL Solver handles these changes by extending the original Lear star theory and provide a novel decision procedure.
Lear star has the star operator as part of its ABC construct. But here you also show a summation. Does it have also a summation operator?
The summation here means the unbounded summation unit pressure and the summation represented by the star operator, because star operator also represents the summation, right?
But it's not the same thing.
Yes.
Is it the same thing?
They are not the same thing. Yeah, maybe it's a little confusing.
Could you share an example where you can translate a summation into a star operator? I can also confuse here.
Okay. I put them in the backup slide because I'm worried we do not have enough time. Okay. Okay, here. We want to prove the distributive law of unbounded summations here. You'll see that maybe this does not correspond to any SQL queries, but I just use this simple example to show how to convert the unbounded summation in unit pressures into the summation in Lear star. Okay, and the distributive law means that the first summation plus the second summation is equal to the third summation here. It is true because they operate on the same domain y, and summation f1y plus summation f2y equals to summation f1 plus f2. Okay, and the first step is that we will first replace every summation with a new variable. There are three summations here: summation f1, summation f2, summation f1 plus f2. So we introduce the V1 to represent the first summation, V2 represents the second summation, V3 represents the third summation, and the formula becomes the axis V1, V2, V3. V1 plus V2 does not equal to V3, but because we this is does not equal to, not equal to, because we want to prove that this is impossible to hold. Okay, and we add a condition to represent that V1 equal to the first summation, V2 equals to the second summation, and V3 equals to the third summation here. So you will see that there is an integer vector now. It has been similar to the Lie star theory. And then the second step is that we can replace the summation symbol with the star operator. The first part is still V1 plus V2 does not equal to V3. And the second part becomes that the vector V1, V2, V3 belongs to a set. And the set, in this set, the set contains elements x1, x2, x3. And we require that V1, V2, V3 should be the unbounded summation of x1, x2, x3. And x1 represents the result of f1y. X2 represents the result of f2y. X3 represents the result of f1 plus f2. So in the original use pressure, V1, V2, V3 equals to the summation f1, f2, f1 plus f2. And in the new generated formula, V1, V2, V3 belongs to a set, and V1, V2, V3 is the linear combination of x1, x2, x3, and x1, x2, x3 represent f1, f2, f1 plus f2 respectively. Okay, and after that, because in Lie star formula, we can only use integer variables. We cannot use tuples, we cannot use functions. So we need to replace these functions f1 and f2 to be some variables. And after we treat f1, f2 to be variables, we will find that this formula, if we treat f1 and f2 to be formulas, this has been a Lie star formula. And we can use existing algorithm to translate the Lie star formula to be a Lie formula here. And V1, V2, V3 equals to lambda 1, 101 plus lambda 2, 011. And this formula says that V1 plus V2 always equals to V3. And the first part says that V1 plus V2 are not equal to V3. So this formula is false. This is a basic process to translate use pressures into the Lie star.
A quick question. So how do you go from the three functions to the linear combination of those two things? Why isn't there a case like 3 zeros or 2 ones and a 2?
V1, V2, V3 can be 3 zeros. If lambda 1 is 0 and lambda 2 is 0. Okay. And lambda 1 and lambda 2 can be any integers. But even if you assign different values to lambda and lambda 2, this formula is still false. Okay. Any other questions?
It's not an easy translation. It's not an immediate translation of summation into star, but I think we got the high level idea.
Yes. They are not equivalent to translation. We lose some information because for this unbounded summation in the use pressure, every unbounded summation should have only one value, right? But in the Lie star formula, we say that it belongs to a set, so it has many possible different values. It can even be 0. This is the gap between the summation in Lie star and the summation in use pressures. And we guarantee soundness rather than completeness. If we prove that this formula is false, then the two sigcores must be equivalent. Otherwise, we do not know whether they're equivalent or not.
I see. So it's a one-way translation.
Yeah. Okay, let's come back. Then I will introduce the three changes. The first change is nested summation. Nested summation means that there are star operators nested in the star operator. This is the formal definition. In the normal form of the Lie star theory, the F2 should be a Lie formula. But if F2 has some star operators, it becomes the nested summation. This can be addressed by the original Lie star theory. And here is an example. You will see that there is a star operator in the star operator here. And the nested summation often caused by the subqueries, join, and some other features. These features are commonly used, so this is very important to address nested summations. And the basic idea is that we can recursively remove the star operators. The basic idea is that we can first find the innermost star operator. The innermost means that there is no star operator in the star operator. Then the star operator is the innermost. So because if there is no star operator in this star in the innermost star operator, we can translate it into a Lie formula, and we can repeat this process. And in this example, this formula is the innermost Lie star formula. So we can first translate it into another equivalent Lie formula shown here. Here means that x3 equals to lambda and x4 equals to lambda. And then you will see that there is only one star operator. This is a normal form of Lie star formula. So we can further remove this star operator and convert the whole formula to be a Lie formula. And this formula can be solved by the SMT solvers, which is false. And the second change is the nonlinear operators. Nonlinear operators means that there may be multiplications between variables under the star operator. This is the formal definition. In the normal form of the Lie star formula, the F2 should be a Lie formula without multiplication between variables. But if it contains multiplication between variables, the summation here becomes a nonlinear summation. And here is the example. Under the star operator, there is a subformula x2 times x3. This is nonlinear. And the root causes is a set operation such as the intersect. And the multiplication between the attributes, which means that select A times B from R. And to address this change, the basic idea is that if we can replace nonlinear operations with linear operations, we can get a Lie star formula and we can solve it. And we address this change by constructing the overall approximation. The formula F1, if the overall approximation of F2 means that F2 can infer F1. So because F2 can infer F1, so if we want to prove that F1 is false, we just need to prove that F2 is false. Okay, so if we want to prove that a formula is false, we can prove that the overall approximation is false. So the problem becomes how to construct an overall approximation without multiplication between variables. The basic idea is that we can replace the multiplication subformula with a fresh symbol y and a constraint. The constraint requires that the new symbol y is 0 if and only if any variables in the multiplication subformula is 0. So in this example, we can replace the x2 times x3 with the new symbol x4 and the constraint x4 is 0 if and only if x2 is 0 or x3 is 0. This looks simple, but it works because in many cases we only care about whether the tuple is in the result or not, which means that we only care about whether the subformula is 0 or not. So this method seems to be simple, but it works. And finally, the third change is parameterize the Lie star. Some variables within the star operator are not integers. They may be string or maybe some other data types. We call these integers to be parameters. And if the formula in the star operator is a formula with non-integer variables, we call that this Lie star formula is a parameterized Lie star formula. And usually the formula in the star operator here is F2. F2 is usually a first order logic formula. And here is an example. Under the star operator, here is the star formula is this variable x3. x3 equals to the string A here. So x3 is the string type. This is not the integer type, it's a parameter. And the root cause of such not parameterized Lie star is that some tables will have columns. These columns are not integer, they're string or some other types. So our basic idea is that because we have Lie star solver, we have SMT solver. Lie star solver can address star operators, but cannot address string or some other data types. SMT solvers can address string and any data types, but it cannot address the star operator. So the basic idea is that we should combine these two solvers to solve the formula. So assume that the formula here is F1 and V belongs to this set, and the formula in the star operator F2 is the first order logic formula. Our first step is that we propose a theorem to move the parameters under the star operator outside. The concrete theorem can be found in our paper, and due to the time limitation, I will not introduce the details. After that, we will construct a new formula F3 in the star operator. Because we move all the non-integer variables outside the star operator, so the formula F3 now is a Lie formula. And then will generate another formula F4 outside the star operator. It contains all parameters. And the F4 is the first order logic formula. And the second step is that because this formula inner the star operator is the Lie formula, so this can be addressed by the Lie star solver. We can directly translate the Lie star formula into an equivalent Lie formula here. So now the formula becomes F1 and F5 and F4. F5 is the Lie formula, F4 is the first order logic formula. So now the whole formula has been a first order logic formula. This can be directly solved by existing SMT solvers. This is our algorithm to combine both solvers to address parameterized Lie star. And because SQL equivalency is a fundamental problem in database research, and it can be applied in many areas, so we propose a system called VTwin. It can automatically discover right rules using the SQL solver. SQL rewrite is a typical optimization technique in database. It will use some rules to rewrite the original query into an equivalent but faster query. So our system VTwin will first enumerate all possible cycles and enumerate all possible pairs of cycles. Each pair of cycle is actually a right rule. After that, we use SQL Server to check whether the two SQL queries in the rule are equivalent. If so, the rule is correct because it does not change the semantics of the SQL query. Otherwise, the rule is not correct. And after this step, we get a set of verified rules. Finally, we use performance estimation to check whether the new query is really faster than the old query. If so, the rewrite rule can actually rewrite the query to improve performance, so we can get a set of useful rules. This is the workflow of our system VTwin. And in the evaluation, we compare our proof SQL Solver to two existing verifiers. One is UDP and one is SPACE. And our benchmarks include 400 pairs of equivalent SQL queries. We do not use non-equivalent SQL queries because we ensure soundness rather than completeness. So it's meaningless to test our solver on non-equivalent queries. And these queries are derived from CalSet and Spark SQL. We also use some rules to rewrite the SQL queries in TPCC and TPCH, so we can construct a set of equivalent SQL pairs. And we evaluate the new discovered rules by VTwin with the Microsoft SQL Server. The first question is that, can SQL Server have better verification capabilities than prior work? And you will see that among the 400 pairs of equivalent queries, we can prove 384 pairs. And we cover all equivalent pairs that can be proved by existing works. We are also the first verifier can pass all test cases in the CalSet. There are also some cases that we cannot prove because we does not support some SQL features used in these cases. And the second question is that can SQL Server help V-Twin find useful write rules? Finally, we discover, okay.
You mentioned there are several features you don't support. Could you mention some you don't support them because they are fundamentally you are fundamentally unable to support, or if it's for some engineering reasons?
I will introduce in the limitation slide. Okay, thank you. And we finally discovered 35 useful rules, and we tested these rules on about 88,000 real-world queries derived from real-world web applications such as GitLab. And we proved that these rules are useful. We find that 9 of these rules are missing in the Microsoft SQL Server, and 22 of them are missing in the concept. And we can use these rules to resolve about 38 performance issues derived from the GitHub performance issues. And you will see that existing database such as Microsoft SQL Server can only resolve 23 performance issues. So this can demonstrate that our new discovered rules are useful. And for the 8,000 queries derived from the real-world applications, we can rewrite about 600 of these queries. And among these 600 SQL Server misses about 200 of them. And about 13% of these queries can achieve more than 90% latency reduction. And we also built some online demo to, sorry. There is some.
You have to drag it. Yeah.
Okay. We built some online demo and welcome to try it online. This is a demo of the SQL Server. You can input the schema of the tables and input the 2 queries you want to prove. After that, you can push the button verify, and it will return the result whether they are equivalent or not. And the detailed introduction is in the documentation page. And we also open source our code in the GitHub. Welcome to help increase the star. And this is a demo of the V-Twin. We discover some new rules, so we construct an online demo to rewrite the query you give it. You can input the schema and the original query. After that, you can click on the rewrite. And after some time, it will give you a query, optimize the query. And this window shows what rules it used to rewrite this query. Okay. And there are some limitations of SQL Server. First, we do not support order-the-back semantics. Order-the-back semantics is a new term introduced in our paper. It means that the result of SQL query is not the result of the query and some ordered tuples. Maybe you can use order by, or you can use window functions to order the tuples in the result. But according to the definition of U-expression, it only represents how many tuples in the result. It does not represent the orders between different tuples. So we cannot support such SQL features. And we need to extend the algebra to support it. And second, because we reuse the part of concept, so we cannot support the dialect or for some other SQL database. And the last limitation is that our algorithm is sound but not complete. Because the problem is undecidable, it's impossible to achieve soundness and completeness at the same time. So equivalent queries may not pass our verification. And because we do not ensure whether the 2 queries are really not equivalent, so we will not also generate counterexamples. And this is the workflow of the V-Twin. And an interesting question is that, could we do more things using this workflow? And this is our future direction. By redefining what is useful write rules, we can do more things. For example, in the materialized view, the database will compare whether the current SQL query is equivalent to some SQL queries that previously executed. If so, it can reuse the cached data for the previous SQL queries. But sometimes, given a SQL query, we find that it's not equivalent to any previous SQL queries. But at this time, we can still do some optimization. We can use the right rule to rewrite the SQL query and change its syntax structures. Then it may contain some different subqueries, and these subqueries can be equivalent to the previous SQL queries. So we can still use the cache data to optimize the performance. And this is an example to use the workflow to do more things. And
for the database folks, this is called semantic query optimization. When you try to rewrite your query to use existing views that have been pre-computed, and you try to use the views instead of going directly to the database.
Okay. Finally, we propose a new powerful verifier called SQL Solver to approve the SQL equivalence. And our source code is open source. Welcome to try it online using our demo. And based on the SQL Solver, we developed the VTwin to automatically discover useful right rules. And we also release our source code and online demo. Welcome to increase our star of the GitHub repository. And thanks for my co-advisors in SJTU, New York University, and Yale University. And my collaborators, also thanks for my collaborators. Thank you very much.
This is great. We have some time for questions. No questions. Yes,
yes, I have a question about your claim about it's sound but not complete.
Yeah.
Because you also mentioned you do some over approximation, right? So if my understanding is correct, the over approximation is basically when you have a join, you are using a set semantics instead of the back semantics. You're translating a application into an OR.
We do not only consider set semantics. We also consider the back semantics. That means that if under set semantics, the method will work. But if you need to consider how many rows in the result, rather than if the row is in the result, the method may not work, but we still guarantee soundness.
So it seems like if your verifier outputs yes, it actually means
they're equivalent.
They're equivalent under the stat semantics.
Back semantic.
But you also. So I'm confused because you mentioned you don't keep track of the multiplicity for your join.
I do not track that, but sometimes the equivalence can be proved without tracking that information. So in these cases, the method will work. Otherwise, the method does not work, which means that I cannot prove the equivalence. Which does not mean that I prove equivalence, but they are not equivalent.
I'm confused.
I think it goes deep into understanding how he converts automation into star, and that maybe you understood it.
I think I can give a quick answer about their confusion. Because in our method, we just replace the multiplication formula to be a new variable, right? So the variable can be any value, but the multiplication subformula can be some values. So the new variable can represent more values than the original formula, right? Mm-hmm. So this is what I mean by over approximation. If this formula is false, when we can get more values, it should also be false when we can get less values here.
I see. Because in your constraint below, you are only constraining the 0 case. So like y can be 2, 3, 4.
Yes.
It's not only the set semantics.
What about outer joins? Do you handle outer joins?
Yeah, I handle. Outer join needs to consider none. This is the main difference between inner join and outer join. Yeah. So we introduce a new predicate called is none to represent whether the tuple is none, and then we can model the outer join in use pressures and further use this algorithm to translate the use pressure into linear formula.
You implemented this in SQL Verify.
Yeah.
Okay. Any more questions? Okay, let's thank Howard again.